Okay, so we learned about energy. We learned about how there's kinetic energy and potential energy. And I also mentioned the key idea for this video is going to be something I mentioned in passing before, which is that energy can be exchanged or traded between different objects and also between different forms of energy. So for instance, kinetic energy can become potential energy and potential energy can become kinetic energy. One very simple example is the example I already used where you lift an object up and then release it. When you release it, its kinetic energy starts to turn into potential energy as it falls, which we'll come back to in a minute. But the key point is, it's not just that energy can be exchanged between different objects in different forms, but you have a, when you do exchange energy in this way, the amount of energy you end up with is always equal to the amount of energy that you started with. Energy is not, let me be a little bit careful, energy is never created or destroyed in a process like that. And this idea, we call this conservation of energy. It's the same idea as we had conservation of momentum earlier. Conservation of momentum is the idea that, you know, if you create momentum over here, you have to create an equal and opposite momentum over here because the total amount of momentum always has to stay the same. The total amount of energy also always has to stay the same. So you can exchange energy between objects, you can exchange energy between different forms, but the energy that one object loses is always going to be equal to the amount of energy that the other object gained. So whenever energy goes down in one place, it has to go up somewhere else and vice versa. And the total amount of energy always has to remain the same. And that's going to be our key foundational idea that everything else is based on. That's one of the key, this is like the equivalent of Newton's laws for the world of energy, is this conservation of energy as being our main guiding principle. Okay, so let's talk about just like a simple conceptual example. Let me use the one that I've been using, maybe pick something that's not breakable. Say I take this object, I lift it up, and then I release it and I let it fall. Let's see if we can describe this process in energy language. Okay, so in this case, when I lift the object up, I give it potential energy. That's going to be potential energy due to gravity in particular. There are other types of potential energy as well. When it starts to fall, its potential energy transforms into kinetic energy. So that potential energy gets released and becomes kinetic energy. And as you know from, Newtonian physics, as the object falls, it accelerates, which in other words means that it goes faster and faster the more it falls. In the energy-based language, the way we wrap our head around that is that as it falls, more and more of its potential energy is becoming kinetic energy. So it keeps gaining more and more kinetic energy, which means it gains speed because kinetic energy is motion. So more kinetic energy means more speed, basically. So in the energy-based viewpoint, we have no concept here of a force acting on the object. Forget about forces. We have no concept of a force acting on the object. What's going on in the energy-based framework is I put in a bunch of kinetic energy when I did this, and then when I release it, that potential energy transforms into kinetic energy. And the lower it gets, it loses more and more and more potential energy and gains more and more and more kinetic energy. So that's why it keeps going faster and faster the more it falls. So you can see this is a very different description of something falling than we gave in the Newtonian framework. But it turns out that it'll produce equally good results once we have the mathematical framework to actually talk about the results, which will be a future video.